Hello everyone, so welcome back to the 154 course. So this is the last topic we're gonna discuss. I'm very sorry that we come until the very end of the semester. Okay, this course is very tough, too many topics to cover. Okay, so nuclear physics. Okay, we're gonna start with the property of the nuclei. We're talking about the binding energies, the nuclear models, radioactivities, decay processes, natural radioactivities, and the last one is nuclear fission and nuclear fusions. Okay, so study from the history of the nuclear physics. Okay, starting from the 1896 when Henry Becquerel discovered the radioactivities. We're gonna discuss about it when we talking about the radioactivities and calculate like half-life or activities, for examples, and then followed by the experiments of the alpha particle scattering on the nuclei. Okay, this is to study the structure of the nucleus. So the experiment conducted by the Rutherford, Geiger, and Marsden. Okay, and after that we have the 1930 Krakow and Walton conduct the first artificial nuclear reactions. After that we discover neutron by James Chadwick. Okay, and then 1933 Juliot and Juliot Curie synthesized the artificial elements first time, and then at 38 so we discovered the nuclear fissions by Otto and Stramans, and after that in 1942 Enrico Fermi draw the first plan for the fission reactors. Okay, and this is what we call the Chicago Pipe 1. And this is a drawing of the experiments. Okay, let's start from the property of the nuclei. Okay, I think this thing it's very common thing that we have learned before. So the nuclei, when we represent the nuclei, we're talking about the proton and the neutrons. Okay, so we use the symbol AXC. So A is the mass number. So this is the total number of the nucleon, which is the neutron plus the protons. We have the C, which is specified by the number of the atomic or number of the protons. Okay, and the X is the element symbols. So the table gives you an examples of mass in different units of different particle or atoms. So like proton, neutron, electrons, or hydrogen atom, helium nucleus, helium atoms, and the carbon atom, for examples. Okay, so we have mass in 3 units. So the kilogram, so this is SI unit, the mass in U. Okay, so we can convert this to kilogram. So 1 U is 1.66 times 10 to the minus 27 kilograms. Okay, or it's equal to the 931.5 mega electron volt per C square. Okay, so you can convert. It's depend on what you're gonna use. So if you use the kilogram, you need to convert everything to the SI unit. If you use the U, basically it's convenient for this case because we represent the we normally use the mass in U to represent the weight of the nucleus or the elementary particles. Okay, but if we're talking about more elementary particle, we talking about the relation to the energy. So it's easier to talking about the mega electron volt per C square. Okay, so it depends on the problem. It depends on the topic that we are using. Okay. So next is the word of the isotope. So I think you know that. So the isotope mean that it's the particle that the element that have the same atomic number. So it's the same number of the proton. Okay, same number of protons. Okay, but different number of the neutrons. So that's make the A difference. Okay, so you have X, C, A. So what is different is A. Okay. However, the chemical property of the different isotopes are identical. Okay, but they often have a great difference in nuclear stabilities. Okay, so some may have the more stability than others. Okay, that we're gonna discuss about that. Okay, but before we go to the nuclear structure and the nuclear activities, so the first thing when we would like to discuss something, we are talking about the size, right? So how can we measure the size of the nucleus? Okay, so that's starting from when Rutherford, okay, create the isolated systems to analyze this thing. So he's shooting the alpha particle or the nucleus of the helium. Okay, so that's when it go to the nucleus. Okay, at one point, at one position, all of the kinetic energy gonna converge to the potential energy, all of that. So the particle gonna stop at some point and then it start to go out. Okay, at that point that it stop, all of the kinetic energies convert to the potential energy. So the Coulomb potential energies. Okay, so if we use these calculations, maybe you should know that the particle gonna the particles stop momentarily. Okay, so the kinetic energy is half of the mv square. Okay, the potential energy is gonna be k q, which is 2e q set e divided by d. Okay, so finally you get the d. Okay, so it's gonna be 4k ce square divided by mv square. Okay, and this d using the gold foil as a target. Okay, so Rutherford's found like d in the order of 3.2 times 10 to the minus 14 meters. Okay, so what does it mean? It means that the nucleus need to be smaller than the 10 to the 14, right? Because the nucleus, the shooting of the alpha particle reach the nucleus, but it cannot really reach. It stopped at some point because of the kinetic energy. All of the kinetic energy convert to the potential energies. Okay, and that distance he found 3.2 times 10 to the minus 14. So he said that, okay, so it's mean that the nucleus side, the nucleus side should be less than 3.2 times 10 to the minus 14 meters. Okay, this is what he get. At the present, so we say that the nucleus is maybe in the unit of the femtometers. Okay, so 1 femtometers is 10 to the minus 15. Okay, which is roughly the same as the size found by the Rutherford. Okay. After Rutherford, there are several experiments come, and then they're trying to measure the radius of the nucleus. Okay, and the conclusion is that the radius is proportional to the constant and the atomic mass to the 1/3. Okay, so this is what they get. Okay, A is constant. The value is 1.2 times 10 to the minus 15 meters. Okay, and A is the atomic mass. Okay, so what does it mean? What does it mean from these relations? It means that if we are talking about the volume of the nucleus, the volume is, if nucleus is spherical, so what you're going to have is the volume is a 4 over 3 pi r to the third, right, to the cube, r cube. So V is basically r cube, which means it's proportional to the A, right? The volume of the nucleus is proportional to the atomic mass. And after that, if we're talking about the density, maybe change the color to get easily. So density is mass divided by volume, right? The mass is clearly atomic mass. The volume is depend on the atomic mass. So it's mean 1. So what does it mean? In this case, so it means that the density of the nucleus is basically constant, okay? Because it does not depend on the mass number, it does not depend on everything, right? So, so what we get is that the rho it's basically constant, okay? But of course, it's not exactly constant. Maybe it's different between size, but between size and mass, when you try to make the ratio, it's not really constant, but it's roughly constant. Okay. So when we have the after that, we're talking about the nuclear structure and the stabilities. Okay. Because in nucleus, it's a group of the neutrons and the photons, right? I use this one as the solid one as the protons and the hollow one as the neutrons. Okay. So, if you try to group the neutrons and proton together, it cannot be explained by the electromagnetic force, right? Because if you have the charge, if you have the same charge, it cannot go close to each other because it's gonna have a repulsive force between the same charge to make it move away, right? But if you have a different charge, it will try to push it close together. It's attractive force. However, nucleus exists, and we know that the nucleus consists of the protons. Okay, so how can the proton stick to each other? And how can neutrons stick to each other, or how neutron and protons stick to each other? We need a new force. And then that new one is what we call the strong force or the strong nuclear force. Okay, it's a force that acts between proton and neutron of the atoms. And this force should override should be superposition, let's say, override or superposition with the Coulomb. Okay? So when we are talking about the size of the nucleus, it's small. So if you're talking about the Coulomb, it's divided by the small number, right? Divided by R. So R is the the distance between two charges. So R is small, so it means that Coulomb is large. But in the nuclear, it's there. So it means that the nuclear force needs to be much stronger than the Coulomb so that it can keep the nucleus stick to each other. Okay? So that is the idea of the strong force. However, if we're talking about two charges, which is like 10 centimeters away, this nuclear force should not act on this length, right? Because if it need to act on this length, two same charge need to go to each other, but it's never, right? If you have the same charges, they have the repulsive force to move it away from each other. And this is the way how we looking on the electromagnetics. Okay. So this strong force need to put in a very short range. Okay. That attractive nuclear force, so enough to overcome the electromagnetics. So the nucleus force can bind and make the atomic nuclei. Okay. So how to study this one? So you can do the neutron scatterings or proton scattering to the target that containing the hydrogen. Okay, so neutron proton scattering on hydrogen target. Okay, so when it's come close to each other, it try to stick it together. Okay, with the lowest potential, it's the distance that's great enough, so system is more or less stable in that distance. But if the proton or neutron start to collapse close to each other, they're gonna face a very strong potential to protect that to happen. So the nucleus never collapse. It's never let's say it's not trying to expand and it's not trying to collapse, because it have the potential that it's stable. So it's there, it sit there. Okay, so it's not trying to climb up in each direction. Okay, so this is the plot between the potential and the distance. So you can see that the size of the potential is roughly a femtometers. Okay, the difference between left and right part is the left one is the neutron and protons. So neutron have no charge, so there are no electromagnetic wave. Sorry, not electromagnetic wave. Electromagnetic force act on this system. Okay. However, if you're talking about the proton, when the proton start to close to each others, okay, they have start to have the repulsive force to push it away. Okay, but when it comes to very close, after less than 3 femtobarns, okay, there are no effect on the electromagnetic force, because it's overcome by the nuclear force. Okay, so starting from this, so the nuclear force overcome electromagnetic force. Okay, so that's why we see different here. Okay, because electromagnetics will have like this. Okay, so this is from the electromagnetic. Okay, and then it's going to be controlled by the nuclear force, and after that, both nuclear and electromagnetic force is trying to push the proton and proton away from each other, which is correct, because the proton cannot collapse into a single point. Okay, it still have the distance between it. Okay, then when we are talking about the nuclear stabilities, okay, the stabilities, it means that nucleus is stable, it's not trying to decay. Okay, so at the beginning, at the very low atomic number C, or the neutron number N, so at the low regions, so the number of neutrons is roughly the same as the number of the protons. Okay. However, when the number of the proton increase, okay, you need more neutrons. So this line called the stable lines. Okay, why do you need more neutrons? because if you have more C, it means you have more electromagnetic force. So when you have more electromagnetic force, you need more nuclear force to bind the nucleus. Does it make sense? You have more electromagnetic force. It's trying to put the proton away from each other. If you want to make a nucleus stable, you need more neutrons so that it increase the strong force so that it can override the electromagnetic. So you need more neutrons. And you ask, can I add more C? No, you cannot add more C, because if you try to add more C, you increase more electromagnetic force. Okay, at some point you increase also the nuclear force, but as you increase more electromagnetic force, that's gonna be unstable, and that you need more neutrons. Okay. Okay, let's continue. Very sorry, there's some accidents of the microphone. So I restart on the nuclear binding energies. Okay. So when we're talking about the nuclear binding energy, what exactly we are talking about? We are talking about a situation that you have, for example, the neutrons and the protons. Okay. And then it start to combine to each other and become a nucleus. Okay. We said we're gonna get that the mass of the instituents, the mass of the component, is larger than the mass of the nucleus. Okay. And the difference of the energies are different of mass, because mass and energy is the same thing, right? So the difference, this is what we call the binding energies. The binding energies, by definition, it's the mass of the constituent, so mass of the proton. So you have C proton with mass of the proton plus neutron, which is A minus C, mass of the neutrons, and then minus mass of the nucleus. Okay, and then you convert it to energies. So you can use C square if you use the mass as the MeV per C square, but if you use the mass as the U units, okay, so you multiply by the 931.5 MeV per C square per U, sorry. Oops. .5 MeV per U. Okay, so you get the energies, and this is the point that so if you have starting from the constituents and then you try to group it together, you're gonna have more less mass on that. Okay, and the mass that what we call deflected, it's gonna become the energies. Okay, and the difference of the difference between mass and different it's what we call the binding energies. Okay, we can convert mass to energy. Okay, the difference on mass, it's for example the delta M, which is mass of the constituent minus mass of the nucleus. Okay, and that convert to the energy. Okay, and this is really a key point of what we're gonna study at the end, what we're gonna learn at the end about the fission and fusions. Okay, but first, before we go to that, let's look on the trend of the binding energies. Okay, so there is a trend of the binding energy per nucleon. Okay. So the binding energy start to increase, okay, when the atomic mass increase, and then when it reaches the point around 60, okay, it's maximum, and then it start to be decreased. Okay, so this is the way that the binding energy per nucleon look like. So we can really estimate that. So if you have, for example, some element with the mass number, you can really roughly say that what is the binding energy of it, okay, per nucleon of it. More binding energy, it means more stables, okay, more or large binding energies, it means stables. So you need more energy to break, okay. So if you're still confused what exactly it means, let's imagine that you have the nucleus and you want to break it, okay, and if you want to break it, you need to put the energies, and then you can break it apart, and this is you need to put it equal to the binding energy so you can break it, okay. Okay, so this is the concept of the nuclear binding energies. Next, now we know about the size, we know about how to make it, write it as a symbol, we know how it's stick together. We now trying to model it, okay. It's the same of the atomic physics. So you try to model the atoms. Now you try to model the nucleus, okay. So there are two models mentioned in the survey. So one is a liquid drop model, another one is shell model. Most of them, they don't really have a computation, but they try to teach you on how the model is motivate, how it's work, okay. So in this lecture, I pick one of that, which is what we call the liquid drop model. Why I need that? Because the motivation of this model is to describe the mass and the binding energy of the nuclei. That's what we are discussing. So in the liquid drop models, the molecule, we try to model the nuclei as the liquid drop, okay, a small drop of the liquids. So in the liquid molecules, they are bound together from the van der Waals force. So for the nucleus, they are bound together with the nuclear force, okay. Nucleus as is considered as a drop of the incompressible fluid, right? Because as you learned before, you cannot really squeeze it, okay. You can squeeze it to reach at some point about half of the femtobarns, and after that you cannot really squeeze it more, because you're gonna have a big repulsive from both strong force and the electromagnetic force, okay. So it's at some point stable at one range, okay. So that's what we consider it as a drop of the incompressible fluid, okay. They have a very high densities, okay, and they act only between the neighbor nucleon. What does it mean? It means that if you have a nucleon, okay, and inside you have neutron and protons, like this, these guys will not talk to this guy. They don't. This blue guy will talk to the neighbor only, so they talk to green, okay. They don't talk to red. So that's what we call the arc between, that's what we say, it's arc only between the neighbor nucleon, okay. As a liquid, so we consider that it have a spherical shape, Okay. So with these considerations, what is gonna be the binding energies? Okay. We want to know about the binding energies. Okay. So first term, it's what we call the binding energy in general. This is the general idea of the binding energy, and then we're gonna subtract it from some factors. Okay. So if we're talking about the nucleus like a larger than, I don't know, 50. Okay. The nucleus is more or less, it has more or less the same number of the binding energy per nucleon. Okay. Just roughly the same. It's 1 mega electron volt, half mega electron volt. It's very small. So the binding energy per nucleon is roughly constant. So it means that the binding energy should depend on the number of nucleons. Right? When binding energy increase, number of nucleons increase, or in vice versa. So both need to be increased together to keep the ratio constant. Okay, so that's why the first term depend on the atomic mass. Okay, the constancy is coming from the experiment, so don't worry about that. Just to get the concept of what exactly the liquid model tell you. The second one is what we call the first surface energies. So if we are talking about the surface here, this red one, you can see that this red one, they are talking only to the neighbor, right? So I overwrite the color. So they're talking about the green one only. They are talking to the green one only. So it means that it will not talk to several of that compared to the, if you compare this blue one, so it's talk to several things, right? It's talk to several nucleon around, but in the border, it's not. I mean, because there are no nucleon outside the outside the volume. Okay, so there are no nucleon here, right? There are no nucleon here. Okay, so it means that the binding energy that we estimate need to be less. Okay, so when we are talking about the surface have the area of the 4 pi r square, right? And we learned already that the r is basically proportional to the a 1/3. Okay, so it means that these binding energies, it's depend on the a to the 2/3, and then it needs to be negative because the volume energy is overestimated because of the surface. They have less nucleon to talk to for the surface nucleon. Okay, so we get this term. Okay, and then we go to the third term, which is the Coulomb term. Okay, so for the Coulomb term, we are talking about the proton. Okay, so you have the proton, which is the red one, so it creates the repulsive force. Okay, so it kind of cancel off the cancellation of the binding energies, because binding energy trying to put it together, but Coulomb force is trying to pull it away. Okay, push it away. So if the nucleus have C protons, how many pair of the nucleus it can create to make the to make the repulsive force. So you start with the C proton, but the proton itself cannot have the repulsive themselves, right? So you have one protons. So if you have another proton, you create one force. You don't create two, because this proton cannot have the repulsive with itself. So if you have the C proton, you're going to have C minus 1 pair, right? Okay. And then the force, it's depend on the R, right? Sorry, the energy is depend on the R. So R is proportional to 1A to the power of 1/3. So that's become the third term. Okay. The fourth term is what we call the asymmetry. So it's coming from the difference between the number of the neutrons and the number of the protons. The difference between number of neutrons and number of the protons. Okay. So we can model it in this way. Okay, but don't worry about the asymmetry and the pairing, which is not exist in the survey. Okay, it's maybe you need more ideas and more deep understanding on that, how to make this kind of term. Okay, but so at least you know about the volume, surface, and Coulomb. This is, I think, simple as you can imagine. Asymmetry, you get a roughly idea of yes, you have the neutron more than that, and that affects the binding energies. Okay, so this is what we call the liquid drop model, so that we can use it to estimate the binding energies. From the experiments, okay, it shows quite good agreement with the data. So when you try to do the experiment and you try to make a fit, you get this curve. Okay, and this curve fit quite well with the result we have. Okay. Okay. So by the end of this video, for this one, first, sorry, because I cannot make a one full record to finish this one. The next one gonna come by the end of today. Okay, I try to finish everything by today, Friday. But let's finish about the radioactivity first for this video. So the study of the radioactivity started in 1896, but it's accident situations. Okay, in 1895, the Röntgen discovered the X-ray. Okay, and in that time, Becquerel, who claimed himself as an expert on the fluorescence, what the fluorescence means is that it's a material that can emit the light under conditions. So you have you have kind of materials, and then using some conditions, you can make it shining. Okay, and that is what we call the fluorescence. So he interested in the X-ray result, and he would like to study that the shining, the fluorescent that he was expert on that can explain. Okay, for example, like his fluorescent, it's basically X-ray or it's not X-ray. So try to study the similarities or difference between fluorescent light he get from the materials and the X-ray. So what he did is basically he chose the material, and in that time the material that quite popular to make the fluorescent is the uranium salt. Okay, people don't know about the radiation at that time. They just know that if some condition, uranium can make uranium shining. Okay, and yeah, they make it like a glass, shining glass like this. Okay, so he make the uranium to be highly fluorescent, and then so this is the uranium. He make it highly fluorescent. Okay, and then in behind it have the like a black box, and they have the photographic plate inside. Okay, and he gonna see that if he can see the spot or anything in the photographic plate. Okay, since it's inside the black box, so it protect the light coming from outside. Okay, so no light interaction on that. However, with the fluorescence or the radiation that he gonna discover can pass through, and it can make the shadow in the photographic plates. Okay, and he see, yeah. So he continue his experiments until one day his uranium cannot shine anymore. Okay, so no shining. So there are non-fluorescent uranium, but he still see that the photographic plate still show the same as the highly fluorescent uranium. What does it mean? It means that the highly the fluorescence maybe not something that cause the spot or the shadow in the photographic plate. It's something else. And what is that thing? Okay, so he's finally he said that yes, this is kind of the new thing. It's new type of the radiations. Okay, and it's no external stimulation. So it means that it can do it by itself. So it's spontaneous. Something happened by itself. Okay, and it can penetrate. That it could darken the protected photographic plate. Okay, and it also can ionize the gas. This is what he get from his result. Okay, this kind of the process, it's what I say already, it's spontaneous process, spontaneous emissions. Okay, and with that what we call the radioactivities. After the discovery of the radioactivities, so on the Paris side, so the investigation by Marie and Pierre Curie, so they both they discovered two unknown elements which can be radioactive. Okay, so in that time they studied the polonium and the radiums. Okay, and continue after that. There is several experiments come later, and conclusion is that radioactivity, it's basically the result of the decay, disintegration of the unstable nuclei. So you have the unstable nuclei, it need to do spontaneous emission to make it stable. Okay, and yeah, if you have chance to visit Paris, you can go to Pantheon, where the tombs of the Marie Curie and the Pierre Curie are there. Okay. Yeah, the Pantheon is sightseeing of the Paris also, and you can meet two of them in the tomb here. Okay. Okay, let's do short calculations. So just to mention first that the decay process is basically probabilistic. Okay, it can create something happen. You don't really know which nucleus gonna radiate. It's random. Okay, and it's described by the statistical calculations. Okay. It's statistical calculations, it's probabilistic. Okay, so what you can do is that you put the amount of the radioactive and then you study on how it's decay, how it's remaining. Okay, so that is what we can do in the calculations. So let's start that you have the starting from the N0, you have N0 atomic nucleus, N0 nucleus, which is radioactive. And then when the time pass, it's some of that radiates, right? And then you have the N radioactive nuclei left. Okay, so you can do dN by dt. So the change of N, okay, it's equal to the lambda, which is the radiation constant, decay constant, times N. Okay, times N. Minus it means that it's reduced. Okay, the number is in the reduction way, in the decreasing way. Okay. Then you integrate from N0 to N of dN over N. It's lambda integrate T0, which is 0 to T dt. Okay. Integrate of dN over N, it's basically natural log. And then this is the lambda T. So finally you get N equal to the N0 e to the power of the lambda T. Okay. So if you would like to find the number of nuclei after the time T, you can use the initial amount of the nuclei, which is radioactive, and then e to the power of the minus lambda T. So lambda is the constant, decay constant. Okay. Since this class we will not have the tutorial class for that, so there are exercises on the survey that you should practice it by yourself. Okay. Great. I think that this topic is easy, but the difficult is that you don't really know what to plug in which. Okay, so this need a practice. So try to do the exercise for this topic. Okay, because we cannot cover it in the tutorial class. I'm very sorry for that. We don't have much time left. Okay, but you can do it by yourself. Okay. And then for the decay rate, okay, so it's what the number of the decay per second, number of decay per seconds, okay, and is defined as the R, which is the size, the absolute of the dN by dt, okay, and it's equal to the lambda n. Okay, and then we solve n already, so it's lambda over n0 e to the lambda t. Okay, and we call the lambda n0 as the r0. Okay, so we finally get the activities equal to the activities in the beginning e to the lambda t. Okay, then we can see that both r and n decrease exponentially. Okay. Next, for the half-life. So half-life, we are talking about a situation when you start from the N0 nuclei and the time pass, and you have the remaining of the half of the original amount. Okay, and this time we label it as a half, like this, t half. So starting from the n equal to the n0 e to the lambda t, right? You can put n equal to the n0 over 2 n0 e to the power of the minus lambda t half. Okay, then you can cancel n. You can take the natural logs. Okay, so it's minus log 2 equal to the minus lambda t and half. So lambda minus cancel, so half life equal to the natural log 2 divided by decay constants. Okay, so now we have it. And at the end, we are talking about the units of the activities. Okay, so they are Curie and Becquerel. For the Becquerel, it's mean a decay per seconds. Okay, but for the Curie, it's 3.7 times 10 to the 10 decay per second. So basically, Curie and Becquerel are the same unit, just the different amount. For Becquerel, it's just 1 decay per second. Curie, it's 10 to the 10 times higher than the Becquerel units. Okay. Okay. So I think we're gonna stop here for these videos, and then we're gonna have remaining the last one for sure. Now we are talking about the decay process, which I need some time to make. I cannot really finish in 15 minutes, for example, because it do take you some time to try to make you understand how things work there. Okay, but it will not be long. I think it's like maximum 1.5 hours for that. Okay, so sorry again for the delay of the videos. Try to finish that. Okay, so let's finish this video now, and then I will continue the recording of the next one.